And also would like to thank for the great opportunity to give a talk at this SIM conference to the honor of Yuri Kabanov. Yeah, so I'm going to talk about some absence of arbitrage theory in the context of large financial markets. This is a joint work in progress with my supervisor, Martin Schweitzer. Okay, so the quick outline of the proof. We start by introducing large markets. Then we need to recall briefly some small market results in order to then being able to introduce new concept and main results in a large market framework. And at the end, if time allows, we present some application and conclude. Okay, so what does a large financial market mean, or large market? Most of you probably familiar with it. Briefly recall, so it's quite simple. We just take a sequence of small markets, by which we mean small market consists of a stochastic basis with usual conditions B, then an modeling asset price process S, where we impose positivity or non-negativity and these non-degeneracy conditions, by which we mean that the whole market capitalization shouldn't jump to zero and shouldn't converge to zero at any finite time horizon. So this is a really minimal assumption. And of course a time horizon which we can take as a general stopping time. It can be in particular also infinity. Okay, so some notations in addition. N denotes the number of assets in the nth market, so it can very well vary over the sequence of small markets. It can in fact converge to infinity, which is a typical application. Then we consider strategies, large strategies, as a sequence of small market strategies where each component should be in some adequate set of strategies. By adequate set here we mean that it's self-financing, so this is a self-financing condition, actually from also presented yesterday in a talk of Martin Schweitzer, and we also require admissibility. And finally, we just simply write zero arrow as a large zero strategy where it's zero in each component. Okay, so some overview, some developments in large financial markets. The origin of this whole framework is due to Kabanov and Kramkov, 1994. They developed some absence of arbitrage theory, which they made more precise in 1998, in fact. And probably the most classical application of this framework is to model bond markets. In fact, if we consider bond markets with maturities in some infinite set, then we of course get infinitely many assets, which wouldn't fit in a classical framework with finitely many assets. So then we, for example, can take large markets and consider asymptotics. Yeah, so there is I would say, considerable amount of literature, not a huge literature on that, but also not small, which we really briefly overview. So absence of arbitrage in the weak sense, by which we mean something like no arbitrage of the first kind or NUPBR, has been developed first, as I mentioned already, Kabanov and Kramkov, then Klein and Schachermayer, as well as later in 2007 by Rocklin, as the work of Karatsas Kardaras appeared, and based on that they improved absence of arbitrage theory. Then in the strong sense, by which we mean in some no free lunch type, I think probably the most important researcher improving this field was Klein in more consecutive papers, and then recently also Cujiero, Klein and Teichmann. And then of course we have utility maximization developed in this field by De Donno, Guassoni, Pratelli, and then later also Raschoni, hedging and pricing, Baren and Roch, and other fields like the transactions cost, Heston type models, and so on. So actually many things has been developed already for large markets. Okay, so we concentrate on the absence of arbitrage in large markets, and then let me recall the classical concept introduced by Kabanov-Kramkov. This is the no asymptotic arbitrage, and this means that the large market with a finite time horizon in each small market admits no asymptotic arbitrage if for any large strategy satisfying that basically the initial value converges to zero, we have that the limit supremum of the probability that the final value is greater than 1, this should also go to 0. So put it in another way, we have asymptotic arbitrage if there is a strategy, a large strategy, which has initial value converging to 0, but nevertheless it's greater than 1 at the end with some non-vanishing probability. Yeah, so this is of course a very nice concept, but it has maybe one major drawbacks, namely that it's not stable with respect to discounting, which I also present in the next slide, and maybe also some minor things that the time horizon in each small market restricted to be finite, and it also does not imply any absence of arbitrage property for the small markets, which you then of course have to assume separately in each small market, which also has been done in the literature. Okay, so the main issue, the non-stability with respect to discounting, we can also present with this very simple example. It's indeed very similar or almost identical to the example of yesterday, and it's also a degenerate example. So one could say it's not proper large financial markets, but it's large financial markets, and of course you could make more fancy examples, but it already does the job. So let's keep it as simple as possible. We consider a Black-Scholes dynamics, two assets. Uncertainty comes from a Brownian motion, as usual. And then the question is, of course, what do we discount by? So we could discount by the riskless asset, or we could discount by the risky asset, or of course we could take any other possibilities. And discounting by the riskless asset, we would write S. Discounting by the risky asset, we write S prime. And then accordingly, we can introduce large markets by S prime, by stopping the asset price at N for every N. And then in this more or less artificial way, we create a large financial market indeed. But since we started by the same dynamics, we expect same economic properties for both large financial markets. Now, what we see is we first observe this small result that a large financial market of the form basically introduces above satisfies NAA, so no asymptotic arbitrage, if and only if the corresponding small market, so we just basically simply take asset price processes before and the infinite time horizon, satisfies NUPBR. So NUPBR is just that the set of final VAS is bounded in L0. So if we have this small result, then we can observe that the dynamics, so the asset price process in the first large market, if for example we take M equal R, it goes to 0, and asset price process in the second market, it goes to infinity. So then it's easy to see that the first small market cannot satisfy NUPBR, and the second one satisfies NUPBR indeed by, for example, the classical result of the Alban-Schackermeier. So then we conclude, due to this simple lemma as above, that our first large market satisfies NAA, and the second one, L prime, does not. which we didn't expect. So yeah. So after this motivation, showing what can go wrong, we need to recall some small market results in order to continue with our results. So the small market framework, let us first define the set of value processes where we consider strategies which are self-financing and admissible. Then we call a semi-martingale, local martingale deflator. If it satisfies this kind of positivity, it's normalized, and any strategy, any value process of admissible self-financing strategy divided or deflated by this deflator is a local martingale. So this is a usual definition. Then we call a local martingale deflator LMD plus if it's in addition satisfies this limit condition. So this is basically that it doesn't make the whole market capitalization disappear. And finally, we call a local martingale deflator tradable if there is a strategy which has a value process which is this deflator. So quite simple. Okay, and we could do the same, of course, for super martingale instead of local martingale, quite analogously. Okay, and then accordingly we write SMD, SMD plus, and tradable SMD. Okay, so no arbitrage for small markets. This is basically really just recalling the definition from yesterday. So we say strategy is index weight maximal if there is, now I only say it intuitively, there is no good, so to say, good portfolio and a dominating strategy such that the dominating strategy at the beginning has almost no more value than theta, and at the end, or asymptotically at the end, it dominates theta plus this good portfolio. So if this cannot happen, then we say that theta is index weight maximal, and then, or no arbitrage condition, the viability condition is we basically say that a small market is viable if the zero strategy is maximal. And here we of course mean dynamic index weight viable, and we say index weight maximal. Yeah, so this is our definition from yesterday, viability, and it has a nice property that it's stable with respect to discounting, and also is strictly weaker than NUPBR, at least in classical models with riskless asset. Now, the results we need from the small market framework is two FTAP type results. First one is that if a small market satisfies that it has non-negative asset prices and non-degenerate asset prices, then we have viability if and only if there exists LMD plus. And the second result is it's actually a generalization of Karatsa-Skadaras 7. And under same conditions, actually, we have viability if and only if there exists a tradable SMD plus. So here, if we compare those two results, here above we have LMD plus, but without tradability, and here below we have tradability, but only an SMD plus. Now, of course, LMD in this framework implies SMD, but not the other way around. Yeah, so those two results, and we, in fact, needed to generalize the results of Karatsa-Skadaras because it has some, so I of course want to point out that, in my opinion at least, is one of the most important results in the later history of absence of arbitrage theory, but it had some certain restrictions which didn't fit in our framework. So, for example, and probably most importantly, it excludes strategies which can default, and then we generalize it also for strategies which can in fact go default. Yeah. So I just probably don't elaborate on this generalization anymore. Yeah, so now we have our small market results, and we can get back to the large market framework by introducing our new concept, the asymptotic dynamic index weight viability, or I just say asymptotic viability. So this is the counterpart of the viability for the small market. And we go analogously, as in the small market, by first saying strategy. So here a large market strategy, of course, is asymptotically index weight maximal if there is a positive P such that for every epsilon there is a small market indexed by n and a set in the small market which has a measure at least P and a dominating strategy which again at the beginning it has almost no more value than theta, and at the end it super replicates theta plus P times the indicator of this set times the market portfolio. So this is basically again our good portfolio. So this is our concept, and then viability, very simple again. We say large market satisfies asymptotically viability, short, if the zero strategy is asymptotically maximal. Okay, so this is our concept, and it has very briefly some favorable properties. Most importantly, it's now stable under discounting, by which we mean precisely that if a large market satisfies this kind of viability property, then and only then any version of this large market discounted by this D, which has this positivity properties, also satisfies our asymptotic viability. So very importantly, and some other features, time horizon can be any stopping time, so even infinity. It has a complete formulation, so asymptotic viability implies viability for each small market, and it also has some consistency property, which I probably won't elaborate on right now. Okay, so let us get to our main results now. This is an FTAP type of result, and it claims that if the large market, such that we have a non-negativity and non-degeneracy in every small market, satisfies asymptotic viability, then and only then we have these dual conditions, which is for every small market we have there exists an SMD plus, and we have this contiguity condition. So it's of course somewhat similar to the result of Rocklin. Now, in order to understand more precisely what does this second dual condition means, we introduce these notions. So psi is we could call it a deflator adjusted by the market volume. It's the initial volume of the market times the deflator, final value of the deflator, divided by the terminal volume of the whole market. So this is our psi, and then psi is then of course a random variable, and then we could define a measure psi times p in this simple way. And exactly this measure we have here above. And then contiguity is in fact one could regard it as a generalization of absolutely continuity. So absolutely continuity, we have two measures. Here we have two sequences of measures, and one of them is contiguous with respect to the other if for any sequence of sets which converges to zero in measure with respect to the second sequence, it converges to zero in measure with respect to first sequence as well. So this is basically some absolutely continuity for sequence of measures. Okay, so this is now a main result, and it gets similar to the seminal work of Kabanov and Kramkov, if we have an equivalent martingale measure, which we in general don't have, but let us assume that we have an equivalent martingale measure, then this part is basically our martingale density, and martingale density times original probability measure is our equivalent martingale measure, right? And then this is basically indeed the result of Kabanov and Kramkov, that we have contiguity between the original probability measure and the equivalent martingale measure. Okay, so I probably won't elaborate on the proof now, and just give an overview of this result. So in this picture, we might understand it a little better in detail. What does it mean? So this is our asymptotic viability, and our main result basically claimed that this is equivalent to this upper part. So this upper part is there exists a tradable SMD plus, and in addition the contiguity condition. So this is further equivalent to the same without tradability. This one can see in the proof, where we notice that we didn't use any tradability in the back direction. So this one is not necessary to imply asymptotic viability. And now the other interesting part is, what if we want to talk about local martingale deflators? So no super martingale deflators, but local martingale deflators stronger. Then the tradable LMD, this won't be equivalent, this is for sure, because it's not even equivalent for small markets. In small markets, we have a nice counterexample due to Takaoka Schweizer in 14, where there's a market which has a tradable super martingale deflator. It has a local martingale deflator, but it doesn't have any tradable local martingale deflator. So these two implications won't be true, of course, also in the large market framework. But in the small market framework, these four guys, of course, without contiguity and without asymptotic part, so these four guys are all equivalent. And in a large market, we have proven these three. And this last one, of course, one implication is trivial, and the back implication we don't know yet. So I try to find counterexamples. I don't want to say how long, because someone else finds a counterexample in half an hour, and then I appear to be not so smart. But so we didn't find any counterexample. We couldn't prove it, so this is still open. Yeah. Okay, and then very briefly we might take a look on some simple application. This application considers again this degenerate case, where the large market consists of a stochastic basis which is constant in n, so all bases are the same, and the time horizon is a sequence of stopping times increasing to infinity, and the modeling asset price process is simply, so Sn in the nth small market is simply a fixed semi-martingale stopped at this nth time horizon. And this, of course, looks really similar morally to the small market, where we simply take B, S, and time horizon infinity. So we expect some similar economic properties, and we investigate this connection between this large market created from this small market in a somewhat artificial way. And there I can give you already our corresponding result, an overview of that. And here we can very nicely compare the classical notions in an asymptotic manner, the classical notions in a non-asymptotic manner, and our concepts. So there are three rows of equivalent notions in a large market sense, in a small market sense, and of course a dual condition. And the first row, the strongest, is a no asymptotic arbitrage in a large market sense. is equivalent to NU PBR in a small market sense, of course, only for this very special large market framework. This is important to keep in mind. And it has then the dual conditions that there is an LMD which satisfies this asymptotic condition. Then the second row, this is basically our new concept, the asymptotic viability, which is equivalent to viability in this special large market framework, and it has the dual condition that there is an LMD plus. And the third row without any asymptotically, so NU PBR is satisfied in each small market, no asymptotic condition. This is equivalent in terms of small market terminology to that if NU PBR is satisfied on every finite time horizon, every actually bounded, so compact time horizon, time interval, and the dual condition is simply that there is an LMD without any plus or asymptotic condition. So the down implications one can readily see by the dual conditions after, of course, seeing the equivalences in the row, because this condition trivially implies LMD plus, which of course trivially implies the existence of LMD. And the upper implications won't be true. In fact, we found counterexamples for each of that. I mean, we only need, of course, 2 counterexamples. So those first row is strictly stronger than the second, strictly stronger than the third. Okay, so there is some slides for the proof, which I again won't elaborate on in detail. And then it's probably time to conclude. So what we have done is we have proposed the concept of absence of arbitrage for large market, which is most importantly stable with respect to discounting. So it doesn't do this kind of interesting behavior as presented in the first motivating example. It can be regarded as a large market counterpart of dynamic index weight viability introduced in the talk yesterday of Martin Schweitzer. And we also has been able to derive a dual characterization and FTAP type of result by supermartingale deflators and contiguity. And there is maybe also room to further research in this area. So as we did the overview of large financial markets at the beginning, we have seen there is at least 2 levels of strengths of absence of arbitrage conditions. We had this NU PBR level, or no arbitrage of the first kind level, and there is this no free lunch level, and this has been covered by Klein, but those notions, of course, are also somewhat dependent on discounting. So it would be a further challenge to develop discounting stable absence of arbitrage notion in this strong sense. And then, of course, it would be nice if it would have a dual characterization, some kind of FTAP results, for example, as in Klein, works of Klein, or as in the recent work of Guillaume, Klein and Teichmann, or of course also some other characterization would be interesting. So this is maybe a further future project. Okay, so I would like to thank you very much for your attention.
Thank you very much for this nice talk. So we have maybe 3 minutes for questions or comments. Oh.
Please show the slide where is the definition of the deflator.
Definition of?
Of the deflator.
This one?
No, much earlier. Much earlier. The deflator. What is the definition of the deflator?
Of deflator? Sorry. Now I understand. Okay. Okay. Yeah.
Okay. So you see that normally the definition traditional definition of a deflator corresponds to one of the D. So the deflator is actually in economics usually a multiplier transforming prices, and so it would be better if you call the deflator value one of the D. This is rather important because you see that from one paper to another, definitions are different. It's very difficult to understand what is going on.
I see.
The next comment is that you call no asymptotic arbitrage, but also there is a certain tradition of in terminology that it is NAA1. Because
yes.
we do not consider here asymptotic arbitrage of the
first kind. Yeah.
And you see that in the theory, actually it is very interesting to see that in fact from one side looks like a symmetry, but in fact it is not completely symmetric.
Yes, this is interesting indeed.
Various reasons. Also, to my mind, is you know that the theory of large financial markets and originally it was a reconciliation of two arbitrage theory. The famous arbitrage pricing model, which afterwards became APT,
APT,
arbitrage pricing theory, starting from arbitrage pricing model, and so this was an alternative to CAPM, because something like security market line appeared. And in our paper, we considered that an example of large Black-Scholes market that also this phenomenon was recovered. And so we used for calculation of actually condition in terms of coefficients, some kind of modification of Hellinger processes theory. So this is, I don't know why, but this this side of the theory, so then we use the calculations, actually is not developed further. So this part, the references were also on the level, abstract level, functional analysis maybe, but not really a stochastic part. So it would be interesting to consider NA2 in the general context.
Yes, it's interesting to know.
And also go further. So just to understand how these conditions may appear, because for economists it was a great novelty that the security market line was not observed, but it was something like a cloud of points near. And this was exactly what this theory can do. Okay, so the consideration, I mean that with APT by Huberman and Ross, and the theory martingale measures, current martingale measures, which was initiated by Harrison and Pliska. This was very important because before it was completely different theory, but this, in the spirit of large financial markets, we can see that one can find something which makes these two theories much more close. This is my basic comment. Okay, thank you.
Okay, thank you for the interesting comment.
Thank you. So, Emmanuel.
Do you have an idea about asymptotic superhedging prices, for instance, under your asymptotic non-arbitrage condition?
Yeah, that's an interesting question indeed. So, superhedging prices has been considered in the context of large financial markets indeed, not by us yet. So it would be, that's right, this concept of us is seems to be suitable to develop in that direction. We haven't done it yet in this discounting stable manner. In no discounting stable manner, as I said, there is some literature on it, so interesting to check it out.
Okay, maybe just one more very short question. So, if not, let us thank Daniel and both the speakers of this session.